In this video, I'm going to walk you through how you can modernize your technology stack with cloud solutions and integration patterns. I am Karina Varela and I work at Red Hat as a Principal Technical Marketing Manager. First of all, we should notice that companies have different concepts about what it means to modernize their technology stack. You can see as the top 3 concepts that customers categorize modernization as the need of containerizing their workloads, automating their operations, and bringing their workloads to the cloud. Also, the top reasons for them to modernize their stack is to increase scalability and reliability. So how can we modernize an existing stack, considering that we have many big applications that we need to bring to cloud environments? There are some different strategies, including lift and shift, refactor and extend, and rewrite, replace. In this solution pattern, we are going to focus on how we can refactor and augment our existing environment in order to bring and add new capabilities to it. But we don't want to impact the existing stack. So how can we modernize it and extend it with low to zero impact on the existing systems? Well, we can adopt the change data capture pattern, which is an integration pattern that allows us to create an event-driven architecture that will have the legacy systems added inside it. And then we will have the capability of adding all sorts of different cloud-native microservices on top of it to bring new capabilities. Let's see this from a practical example. Let's look at the story and challenges of the Green World store. They are a retail store that sells plants, and they are in the market for over 15 years. The problem is that they are not able to keep up the pace of the high-tech competitors. Some new features they would like to add to their stack, if they could, would be to add a new cashback system for the customers and to have better ways for customers to search for their products. Although they don't have the code for the current production software, and they don't want it to be stopped or interrupted in any how. So if that happened, they would lose a lot of sales. Okay, so how can we add a new cashback functionality where every new purchase is rewarded as a proportional amount of the cashback value of the customer expense? How we can add new full text search capabilities to the products that are maintained in the legacy database without having eventual consistency problems? And how can we bring this system into a modern cloud technology and architecture? So first, we should look at what they have. So their existing architecture is based on a single application that connects to a database, the Retail DB. How can we enhance these search capabilities? How can we offer a new cashback functionality? We should notice that we cannot change the legacy code. The new services will depend on the data that will still be managed in the legacy systems. Also, this data between the legacy and the new services, they must be consistent. Finally, we can use this opportunity to increase the cloud adoption. So what are the challenges in this modernization path? Well, first of all, we should avoid the anti-pattern for data access and management in a distributed architecture, where we have multiple systems managing data in a single database. That's not good. We also should avoid the dual write anti-pattern, because the next thing one might think is, well, I can have my retail service saving the data in the local database and in multiple data stores. Even if the code was available for change, this is not feasible, since this is yet another anti-pattern. So in order to solve this, we can adopt a composable architecture where our independent and event-driven services will add these capabilities without impacting the legacy stack. So this is how it will look like. We will have the retail database and application here, And all our new functionality will be added on top of these two contexts, the cashback application context that persists and manages its data in its own database, and the search application context that also has its own data store, which for this scenario would be best to be some index searching tool like Elasticsearch. This is how the change data capture integration pattern can help us achieving this goal. By using technologies like Debezium and Kafka Connect, we can plug into the database of the legacy system and track all the changes that happen in this database. Debezium will track them, and not only track them, but stream these as events. So all the changes are going to be published in topics within a Kafka broker. With these events being pushed to Kafka and being available for other service, then we can do all we need in order to develop the new capabilities. So Debezium is the technology that will ensure that we will get all the data changes. And not only that, but all these changes will be produced with very low delay. We won't need to change the existing application service data model, and we will capture operations like include, update, and delete, besides capturing old record state with additional metadata. So if we were to look at the final solution for both capabilities, this is a simplified architecture representation that shows how it would work. First, let's say on the enhanced search capability, if we have a new product persisted into the retail database by the legacy service, Debezium would track that change and push the events to a Kafka broker. Based on that, we could use an integration service developed with Camel on top of Quarkus to subscribe to the topics, get the changes, process them, and save them into Elasticsearch. Then we would be able to expose it with a new UI, if that was the plan. For this demonstration, that would serve our need, just to visualize the data that is coming through this event-driven solution. Now looking at the cashback functionality, we need something more robust, since all the data that is coming from Debezium will be a change for every line in the table. The data for sales is stored in multiple tables, in two tables, the sales table and the line items table. So then, instead of directly getting these events and adding them to the database, first, we need to get these changes and work with this data. So using Kafka Stream, we can filter data, aggregate them, enrich them, and publish a new version of these events that can actually be consumed by another event-driven service that is implemented with Quarkus and Camel that can contain the logic for the cashback calculation. So once this service is notified that a new expense is available to be rewarded as a cashback, it will get these events data, process it, and sync the cashback database with it. Finally, we can expose this in multiple ways, either using mobile applications or web applications. For our scenario, a simple UI can do the trick. So let's see how we deliver the search index capability that is described in this diagram. So here I have my container as a service solution. I have the OpenShift container platform that allows me to deploy all my services. Within it, I have Elasticsearch, I have Kafka streams running, I have my UIs, and so on and so forth. So let's take a look at this. First, I will get the routes to access my service. So I can come to the route section and I will open the search service. The search service is currently gathering data from Elasticsearch. So this data is already synchronized from the legacy database in the new Elasticsearch data store. If I were to search something like Distrito Federal, which is a city, the capital of Brazil, I cannot find anything. So let's add a new product to the legacy database and see if our services will react accordingly. The first thing I need to do is to access the legacy database that in this demonstration is running in a pod inside my OpenShift cluster. This could be running on-premise or wherever the legacy scenario brings us to. Since I am now in the Postgres container, I will access my database, and I can see that I have my products table. Let's insert a new product. We are going to add a product called the golden leaf cactus, and this is a rare plant that is produced here in Distrito Federal. I have added it, so what should I expect to happen? Debezium will track this change, push it to Kafka, and then we should consume it, okay? So let's see this in action. Let me open CafDrop, which is an UI that allows me to see the messages inside the Kafka topics. And if I open the updates on the product table, I should be able to see, let's just change the offset so we can see the latest versions. I should be able to see that Debezium already streamed the create operation from the Postgres connector with all the information here. With this, the service that is currently running in our OpenShift, which is the Elastic connector, will do the trick. It is listening to this topic and persisting data in Elasticsearch. So if I search now for Distrito Federal, I should be able to see it listed here. So with this, we have added the first capability, the search product capability. With this, we were able to add the first new feature without changing the legacy environment. That is the enhanced search possibility, this enhanced search capability. Let's move on with the explanation of our architecture solution. This whole scenario is implemented on top of Kafka. So we need a reliable Kafka that is highly available for us to use. But let's say that in this scenario, the personnel is not yet capable of dealing a technology like Kafka yet. They do not have the time nor the abilities to do so. Instead of having the operational costs and added complexity of implementing Kafka in our local premises, we can delegate this responsibility to someone else. In this scenario, we can leverage cloud services for delivering this event streaming capability. The name of the service we are using is Red Hat OpenShift Streams for Apache Kafka. If you go to red.ht and open Try Kafka, you should already go to a page where you can easily get started and provision your own cluster, your own instance of Kafka. I currently have provisioned one instance of Kafka, and this instance contains all the topics that I created using the ROAS CLI. I have also configured the access to these topics using ROAS CLI as well. We have some metrics that can help us identifying what's going on. We have the list of topics, and we have all the access configuration available for us to customize as needed. So I have given access only to my service account. That is also available in this managed service. This managed Kafka allows us to have a unified experience across all the clouds, since you can deploy it in multiple environments. Plus, you have it fully hosted and managed by Red Hat, with a 24/7 global support and a 99.95 service level agreement SLA. Let's move on and talk about the cashback solution. In the cashback solution, as I mentioned before, we will get several events that are related to the same sale, although they are not ready yet to be processed and used by the service that actually implements the cashback logic. We can prepare this data by executing complex operations like mapping, filtering, joining, aggregating, and processing the data that's coming in order to publish events with enriched data. By using this API on top of Quarkus, you can even leverage native compilation for serverless architectures. And this is how the cashback solution is going to look like. After a new sale is registered by the legacy application in the retail database, the BZM will track the changes on the two tables, sales and line item, push them to the Kafka broker. Our Kafka stream service is going to listen to those changes and enrich the data as we've just discussed. Next, the event-driven cashback microservice, that is the cashback service, is going to get the enriched data from the event that was published by this Kafka stream service and is going to use it to apply the cashback business logic. This should then be synced to the cashback database that can then be exposed by the cashback service UI. So let's see this in action. The cashback service UI allows us to see everything that is currently within the cashback database. And as you can see, we already have some customers that own some cashback. Although Lena Brock, with this ID, doesn't have any cashback yet. So let's do some simulation so we can act as if Lena Brock is now purchasing new plants in the Green World store. In order to simulate that, we can use this service API to persist new sales in the legacy database. So in order to persist new sales for this customer that has the ID 1002, we can just modify the customer ID and say that this person has just done 10 new purchases. She has gone to our store and she bought stuff in there like 10 times. What we should be able to see now is all the traffic that will happen due to the operations done by Kafka streams. So once this service gets the events from the BZM, it will process the data, the event data, and publish it to retail sales aggregated topic. Let's take a look at it. So here I have some previous data for the other purchases that happened, but we also have the purchases that were tracked and processed by the Kafka stream service and published to the sale aggregated topic. The next thing that should happen is that this service should also notify the cashback connector by saying, hey, there's a new sale ID. We already have all the data streamed in here. So the cashback service is the next to act and execute the operations on the cashback database. With that, if we go back to the cashback service, we should already be able to see all the cashback credited to her as appropriate. Based on her customer status, she gets a percentage of her transaction amount, and it all adds up to a total of $72 that can be used as a discount on her next purchases. In order to build all of that, we need a solid foundation for this solution. And the Red Hat Application Foundation is the one that brings together all these solutions for building, integrating, and deploying and managing the apps from development to production. This whole solution was implemented using Linux, especially containers, on a hybrid model cloud where we have our OpenShift running in one cloud and we have our managed Kafka streams running in another cloud. Next, we were able to build and modernize the apps. We could also connect and extend the apps with solutions like Quarkus, Camel, Kafka streams, and much more. In order to learn more, you can try out the managed Kafka service by yourself for free, no credit card required, by accessing red.ht/trykafka. You can also see the whole documentation about this solution implementation with detailed explanation about everything you just saw. Plus, you can run this demo yourself. So go ahead, learn more, And let's keep in touch. Thank you for watching.